We are talking about logarithms for this lesson, and how to change them back and forth between the exponential equations that you're probably a bit more comfortable with. First off, let's discuss how you even say logarithmic equations, how you speak logarithm, I guess you could say. Looking at this equation that we have here on the left, the way you would say this is log base A of x equals y. Every log has its own base, so you want to specify what base each log has. Again, the way you would say this is log base A of x equals y. So you're saying I'm doing a logarithm, it has a base of whatever, in this case a, because we're just being generic. It has a base of whatever. Then you want to state what you're actually taking the log of, which is what x is representing. And then of course you just, equals whatever it ends up equaling. So again, third time, log base A of x equals y. Okay? Now, moving past that, if we have a logarithm, we are able to take that logarithm and we can express it as an exponential as well. And vice versa. You can take an exponential and express it as a logarithm. Okay? They are meant to be inverses of each other. Logarithmic functions, logarithmic equations, and exponential functions, exponential equations. So, the way that works, the way I've always taught it, is you've got the base of your log, and the base of your log will also be a base in your exponential form, right? Notice that we kept a as the base in both of these. And then what I kind of say is whatever is by itself in one form will be with the base in the other form. Meaning, notice how in our logarithmic form, y is just sitting here off on its own. That's whatever the equation equals. But in exponential form, y gets to be with the base, gets to be with something on the left side of the equation. Whereas the x that was with the base, because it's what we were taking the log of on the left side, actually I'll do a different color. The x that was being with the log, because we were taking with the base, we were taking the log of that x, it is going to be by itself on this one. So that's kind of how I say is your bases stay bases, and then you just kind of switch places with your other two terms. Whatever was with the base will be on its own on one side of the equation in the other form. So let's look at an example here. Okay, let's say I gave you the log base 2 of 8 equals 3. Okay, now to be clear, we're not solving anything here. That's already solved, right? I'm telling you the log base 2 of 8 really does equal 3. I just want to express this in exponential form. So the first question to ask yourself would be, what is the base of that log? Well, the base of this log, and I said it out loud, log base 2 of 8 equals 3. The base of this log is 2. So that's where I would start with writing my exponential form. I'm going to write my base of 2. It needs an exponent though, and I need to choose between the 8 and the 3. Well, like I said, whatever is by itself in one form gets to be with the base in the other form. So I notice that 3 is by itself in the logarithmic equation, which means 3 should be the exponent for my base in the other form, my exponential form. And that means I'm left with it equaling 8, which, as we know, that is a true statement. So, 2 to the third really does equal 8. I feel pretty confident we did that correctly. Like I said, you can also do this the other way around as well. Let's say I gave you 3 squared equals 9 and asked you to write that in logarithmic form. Well, obviously, we're going to write a log then for it to be a logarithm, but we'd want to determine what the base of that log is going to be. Well, looking at my exponential form, I can see that I've got a 3 here that has an exponent going to it. So I'd want to treat 3 as my base, meaning 3 will be that smaller number, a little bit lower than the log, that subscript. Then I want to figure out what I'm actually taking the log of. It's log base 3, not of 3. So if it's log base 3, I need something to take the log of. I notice that 9 has been sitting by itself in the exponential form, so that means it should be with the base in the other form, in my logarithmic form. So that must mean I'm taking the log base 3 of 9. And so then all that leaves us with to set it equal to is the 2. And that is a true statement. I know that one is not one you probably know off the top of your head, but if you happen to have a calculator that will let you type log base 3 into it, then you could verify that that does work. Now, while that's great, let's talk about what we could actually use this for. And what I just said kind of leads into that with the calculator. Depending on the calculator you have, you may or may not be able to do all the different types of logs. Some of the more basic scientific calculators, they have one log button, and it only does log base 10 and won't let you change the base. So, in the scenario where maybe you don't have a calculator available to you that will let you change the base of the logarithm, or maybe you have a teacher professor that is purposefully telling you can't use a calculator to try and solve out a log, let's talk about how we could use this ability to change forms to maybe help us solve out logarithms if all we have is our brains to help us. Let's say I asked you to find the log base 2 of 32. That's all I gave you. I just said, please figure out what the log base 2 of 32 is for me. No calculators were allowed, nothing except pencil and paper. Well, it's very likely that you may not know the answer to that just off the top of your head. And so, as we do in math, when we don't know something yet, we put a variable for it. A lot of times we will commonly use x as our variable, but you could use anything, right? You could use the y if you wanted to. You could use some just random symbol if you prefer something different than the American alphabet, or the English alphabet, I mean. It's up to you. So let's say we don't know what this is yet. We can put this in exponential form. I have a log with a base of 2, so if I wanted to put this in exponential form, I'd also be using 2 as my base there. I notice that x is by itself, that x that we brought in to represent what we don't know is by itself, so that means it should be representing the exponent in my other form. And then that would be equal to 32. Now, this would still require a bit of effort on you guys' part, depending on how good you are with exponents, but I think it is certainly much easier for you to be able to figure out 2 to what power gives you 32 than to do the log base 2 of 32 just off the top of your head. Many of you may already know what power of 2 gives you 32. If not, you can always just multiply it out by hand, right? 2 times 2 is 4. 4 times 2 is 8. So now I'm up to 2 to the third. 8 times 2 is 16, so that's 2 to the fourth. And 16 times 2 does give us 32. So 1, 2, 3, 4, 5 2's. So that means 2 to the 5th power gives us 32, meaning that the log base 2 of 32 is equal to 5. That is something that we can use this changing forms to help us be able to solve out. It can also show you how some logs become extremely simple to solve. For example, let's say I asked you to find me the log base 4 of 4. Well, you may have a guess as to what that would equal, but you may not be 100% sure. Let's talk about what this would look like in exponential form. So again, we don't know what it equals right now, so we'll just set it equal to x or some other variable. If we put this in exponential form, I have a base of 4, so that's where I'd start with. And then since x is by itself in one form, it should be with the base in the other form, making it my exponent. So I've got 4 to the x power is equal to what I've been taking the log of, which is also 4. Well, if 4 to some power is supposed to stay equal to itself, I think that's pretty clear then. X has to equal 1. Right? There's no other exponent that would work because it has to stay exactly the same. So 4 to the first power is just itself. Meaning, what we can extrapolate from that is that any log where the base matches what you are taking the log of, meaning if we had the log of a base a, that's always just going to simply equal 1. It's a nice little trick. Another thing that can be nice to know, think about if I asked you to do the log base 7 of 1. Well, we don't know what that equals right now, and if we put that in exponential form, we'd have a base of 7 to the x power equaling 1. Well, if you know your properties of exponents from our previous video, then you know there is a property that specifically says anything, any base to the 0 power will always be equal to 1. Anything you can imagine, if you take it to the 0 power, it should be giving you 1. So in this case, x must be 0. But more importantly, what I really want you to understand with that is if any base to the 0 power equals 1, then that means anytime I am taking the log of 1, you can pick any base you could possibly imagine for your log, and your answer is still always going to be 0. Log of 1, no matter what the base is, will always be 0. Let's look at one more type of problem. Let's say I asked you to do the log base 5 of 5 squared. Now that's kind of weird because it looks like we have too many pieces here, because if we set it equal to x, it looks like we have 3 numbers and an x to move around. But the catch is you want to treat 5 squared as all one term. So 5 squared is all one piece, and then we've got our base, and then our lonely number on its own. And so if we look at it that way, then changing this to exponential form would give us a base of 5 to the x power is equal to 5 squared. Well, if it's 5 to some power is supposed to be equal to 5 to a specific power, in this case 2, if the bases are the same, the exponents kind of have to be the same as well. So when we write it this way, I think it becomes reasonably clear that x would have to be 2 to have both sides be equal to each other. Meaning, when you have a base that is the same as what you're taking the log of, if you have an exponent, it's just going to be that exponent. It's almost like everything else just kind of disappears. It's not that it's canceling out or anything, but that's what it kind of looks like. These are just some shortcuts that if you understand how to change from logarithmic to exponential form, they can make your solving much, much quicker. Maybe to the point to where even if you have a calculator, you wouldn't want to use it because it would actually take longer to use the calculator than to just use your brain.